Good morning to all of you. I, Akash Sharma, on the behalf of Midas IT, welcome you all to this webinar on consolidation analysis using Midas SoilWorks. For today's presentation, we will talk about consolidation analysis in SoilWorks, the preliminary analysis, an introduction to it, 1D consolidation analysis, an introduction to the theory and demonstration part, finite element analysis, introduction to the same, and the demonstration. So to start with, first of all, what is consolidation? Consolidation analysis addresses the reduction in excess pore water pressure, resulting in increase in effective pressure with time, leading to settlement. Now, there are three types of analysis. First is the preliminary analysis, second is the 1D consolidation analysis, and third is the finite element analysis, which is basically the 2D analysis. So the analysis types, as I described, is 1D consolidation based on Terzaghi theory, the finite element analysis, and the preliminary analysis. Now I will take each of the analysis in brief. So first of all, about preliminary analysis, a number of factors exist in design of soft ground, and most important design factors influencing the magnitude of settlement are consolidation properties of soil, thickness of soft layer, embankment height. Now, preliminary analysis is 1D consolidation analysis performed while parametrically reflecting these three influential factors, thereby enabling the user to readily analyze the settlement trend. So it is basically a first-hand analysis which will give you an idea of how the settlement trend is going to happen. For example, the composition of model is like soft clay. So you define soft clay thickness of zero point 0.2, zero point 0.4, 0.6, 0.8, and 1, embankment of 0.0, 0.5, 1, and 1.5. Now you can check it for both top clay and bottom clay. So in total there will be 30 cases generated automatically by the program, and without much analysis time it will automatically give you an output which will consist of the total settlement, consolidation time for each embankment layer thickness, improvement period, and underground water condition. So you can check that, for example, the consolidation period for the embankment layer thickness 5. So which are the layers which are having the degree of consolidation 95%? So what is the day required for a uniform thickness of the soil? Thus giving you an idea to go for what depth of uh, embankment layer at once, or what amount of loading to apply on the soft ground. So it is basically a first hand analysis performed just to give you an idea of the settlement trend that is going to occur in the soft ground as a result of consolidation. Now, talking about 1D consolidation. Now, 1D consolidation is completely the theoretical uh, consolidation analysis which we have studied in the textbook method. Now, for settlement calculation method, for cohesive soil, we have the delta E method, CC method, and MV method. And for sandy soil, where immediate settlement is going to take place, you have to consider the DBR method and the BK Hogg chart method to consider the settlement of sand, because sand is not going to show any kind of consolidation. It is just going to show you immediate settlement. Now, intuitive modeling features. When you deal with 1D consolidation, you have practice oriented drainage types like PBD, SCP, sand packed drains. Okay, and consideration of CM smear effects can be considered while considering such types of drains. And also in the arrangement type, you can consider the quadrilateral and the triangular type of arrangements. Now, the type of drains which are available with Midas SoilWorks performing 1D consolidation analysis is PBD, that is the plastic board drain type; SCP, the sand compaction piles; GCP, gravel compaction piles; SD, that is the sand drain; CD, cylindrical drain; fiber installed vertically; and the packed woven geotextile back columns filled with sand. Now, the effect which could be considered while considering this type of drain is smear effects. Smear effect is nothing but the disturbance effect. disturbance effect considered delayed consolidation due to the degradation of the coefficient of consolidation from soil disturbance. Now, drain resistance considers the phenomena for delayed consolidation due to the degradation of the flow ability of the vertical drainage as the consolidation progresses. So, both the kind of effect could be considered while considering such type of drains. Next, the boundary conditions which we'll be using while doing or performing the 1D consolidation is change in drain property, strength increase zone, and you have to determine the settlement calculation position, which becomes very important with 1D consolidation analysis. Now, in the results with 1D consolidation analysis, you can check the settlement based on stage embankment when you are creating the embankment in stages, change in soil strength due to the drain placement, the effect of the drains on basically the consolidation, and the residual settlement check based on the preloading. So if we highlight the main features of 1D consolidation over here, so we can say that it helps in calculation of strength increase by loading stages. Secondly, calculation of stress increase by the Bossing's equation, calculation of secondary settlement, calculation of soil coefficient by ground layers using the E log P log MV log P and log CV log P curves. Okay, then calculation of consolidation settlement and immediate settlement, and the settlement reduction reflecting SCP or GCP, in which the smear effect and the well resistance can also be considered. So the design application areas, the primary and secondary consolidation for soft clay, where immediate settlement in granular soil, calculation of the construction period on stage embankments, 1D consolidation slope coupled analysis, drainage functionality check, and calculation of the preloading height. Now what I will do is that I will move on to the program to solve an example in 1D consolidation analysis, so as to make familiar with you with the general workflow uh, in MADAS SoilWorks. So when you start, you have to select the soft ground module in MIDAS GTSNX, in MIDAS SoilWorks, which is basically the 2D geotechnical solution. Now for geometry, you can use the basic line commands, which generally works as per the AutoCAD environment. For example, if I have to create a line, I will say just say 0, 0 and 10, 0. So my line will be created. So similarly, you can create any sort of geometry. Even if you have the DXF file, what you can do is you can go to SoilWorks icon, say import, say CAD file, which is DWG DXF. You can just select the DXF file and say open. Okay. Now when you define the ground material property in 1D consolidation analysis, so you have to select the embankment, sand and clay type. The rest are, you can see that modified cam clay more column are basically for the finite element analysis soil model. So clay, so you can see that what are the input parameters you have to give: the unit weight, saturated unit weight, cohesion, internal friction, the permeability values, the SPT value, which method you want to select, CC, delta E, MV, and then you have to define the parameters. So what I can will do is that if you have already defined the material property, you can directly import it. To import, go to soil icon, SoilWorks icon, go to import and say import database from another file. You just need to select that particular folder in which you have kept the model file. So I'll just select any one and just say import data. Okay, now if you see that the ground material property has already been imported, so we have embankment which will be doing the stage construction, that is in construction stages. We want to check that how with each stages the settlement is happening and how much settlement is happening after some period of time, and also study the influence of drains. So you have the upper clay, lower clay, sand 1 and sand 2. Okay, so having defined the material properties, the next stage is generation of smart surface. So just go to geometry and say smart surface. Now smart surface helps in automatic generation of surface by the program, so which helps a lot of time when you perform the 1D consolidation analysis. And especially you need not select each curves and basically generate the surface. Smart surface will automatically generate the surface for the all the enclosed profiles. So next we have to assign the material property. So whatever ground material property you have assigned will come on the left hand side. Select the particular surface layer. This is sand 2, which is my bottommost layer. Just drag and drop. uh, Once again select the other layer. Once again sand 1, drag and drop. Select all this layer. This is lower clay for us. Then we have the upper clay. Fine. Then we have the embankment. So I will select all the 3 embankment and just drag and drop. Now the important part is we have a lot of surface generated over here. We should be able to recognize basically which is my particular layer. For example, most important will be the embankments. I will tell you why. Because at the time of construct definition of uh, construction stage, you should be able to differentiate between the layers. So it will be more clear when I will show you how to define the construction stage. So first is embankment 1, second is embankment 2, and finally you have the embankment 3. Fine. So these are the 3 embankments. Uh, Now the next step is we need to define the drain property. So I have selected or I have imported the PBD type of drain. Fine. So these are my drain. We are going for a quadrilateral arrangement with center of center spacing being 2 meter, and we are considering drainage and smear effect using the Hansford relation. Okay, now as I told you in the presentation, you have to consider 3 types of boundary conditions. Strength increase zone, where we are basically going to place the drains. Change in drain property, once again the surfaces which are going to where you are going to activate your drains. And the settlement calculation position, basically since it's a 1D consolidation analysis, you have to tell the program where exactly you want to perform the calculations. Okay, so first, strength increase zone. So just give it a name SIZ, standing for the strength increase zone, and select the surfaces. So these are the surfaces which will be having the strength increase zone boundary condition, and just say OK. Once again, 1D consolidation, change in drain property, basically where you want to apply the drains. So I'm just giving it a name drains. So this surfaces and this surfaces. So drain property PBD. So just say OK. Next, you need to define the settlement calculation position. Always remember that you can define as many as calculation position, but for now I'm taking the most critical one, which will be at the center, right? Because the maximum loading will be coming at the center at this particular location. So you can see this line. So if you define the distance increment in number of calculation position, you will have similar vertical lines where the calculation will be done by the program. I'll just say OK. So I have defined the boundary condition. Next, we need to define the water level. So we'll just say water level. I'm selecting this topmost curve as my water level. Select the curves and just say OK. Next thing, we need to define now the construction stage, in which we are going to activate the embankment. For doing that, you go to analysis design, you go to construction stage, analysis type, select it as 1D consolidation. 1, 2, 3 will be the number of step, and just say OK. Fine. Now in the first step, basically what is the construction duration? Construction duration is basically the duration in which you are going to create the embankment, let's say 76 days, and leave time is basically the time after the construction which you are leaving it for the consolidation to take place, let's say 150. And just say add, say first say modify, and the second stage, once again let's say 60 days and leave time being 90, say modify, and the third stage will keep as 60 again and leave time as 150. Now define construction stage. Now in the first stage, activate all the surface. That's why I would say that naming becomes very much important. So we'll not select embankment 2 and embankment 3, but rest of the surfaces. We'll activate both the drains and the sulfate. So apply. Now let's suppose if you want to compare with drains and without drains, what you can do is that you can just deactivate this boundary condition in the second model. So you can just copy this model, but in the second definition, you need not activate it, you just deactivate it. So I will show you results in which in the same model I have one with drains and without drains. So I will explain the results, that how the drains are affecting your consolidation. So say apply, then move on to second stage, activate embankment 2, say apply. Construction stage 3, activate embankment 3, say apply. So close it. We have defined the analysis case. Now just go to analysis case, click add. Method will be construction stage analysis. Give it a name CS. Now maximum calculation days will be basically, we have defined a particular leave time after the construction stage, but let's suppose if you want to see what is the settlement coming after 1000 days or 2000 days, so you have to input that number of days here. Settlement calculation method is basically total load method, means initial load plus whatever load is coming will be added. But if you want to study the load influence separately, you can go for individual load method. Okay, and you have to define the initial water level at this particular location, which is water level. Say okay. Now you can close it. Say analysis and report. You can save the file at particular location. Fine. The analysis will be quick because it's based on simple theoretical formulas. Now let us see the settlement curve. So you can see the settlement curve. So 0 to 76 is basically the construction period. So you can see that there is a in the load, you can see that there is a linear increment, but you can see some consolidation or the settlement curve for this duration. Then there is no load for this particular region, which is like 150 days, which was our leave day, but you can see that there is some amount of settlement. This is particularly because of the consolidation happening. So you can see it is 0.41 when the load, means when we have stopped the construction and we have left it open, and till the next loading it is 0.69. So once again, due to the loading, there is an increase in the settlement, but once again you can see when we have left it, there is some consolidation. So this is how it goes, and you can see that 436 was that we finally left it to 586 days. So this was our final consolidation, but we want to check at 1000 days, so you can check for 1000 days also. So check the value, you can get it in Excel format, and you can just export it to Excel to get a better idea of what. So you can see that at the end of 1000 days, the total settlement is 1.1076. So this is curve, and the rightmost is the same thing elaborated in table. Then you have consolidation settlement table. This is basically for this particular line. As you know, all the calculation are for this particular line. You can see that we have some primary consolidation and some secondary consolidation which can be checked for. Curve for degree of consolidation, as I have already explained you this curve with load, how basically it is changing. Fine. So as I told you that you can create two models, one with drains and without drains. And finally, what you can, I will just show you a comparison. It's the same model, but one is with drains and without drains. Now you can see at the end of 1000 days, this is without drains, the total degree of consolidation which is happening is 85%, or the settlement is 0.09451. Now the main purpose of drains, as you know, is to increase the rate of consolidation, right? So what we did, you can see we inserted the drains which were PBD, and what we achieve is at the end of 1000 days the settlement is 1.19, which is almost 99.95% of the consolidation that is going to happen. So this is how you can increase the rate of consolidation and make sure that there is no long-term settlement in the model. So this is how you proceed with the 1D consolidation method. So hope it is clear that how you proceed with the general workflow. Okay. Now moving on to the presentation part. Next we'll move on to the finite element analysis. Now till now we have dealt with 1D analysis. Now finite element analysis is basically 2D, where if the settlement is happening, it will be occurring in 2D, not in only in the vertical direction, but in both the axis of the 2D interface. Now, in the finite element analysis, Bayot has formulated the theory of coupled solid fluid interaction applied to soil mechanics. Ground is treated as a porous elastic solid, and the fluid in the pores is coupled with the solids based on the condition of compressibility and continuity based on the equation as shown in the screen, where K is basically the bulk modulus of the ground and P is the average total stress. Now, the properties of consolidation elements, the most important variables which is commonly sought in the finite element solution of consolidation analysis are: first is displacement and second is the pore water pressure variation. Now, boundary condition. Now, in consolidation analysis, element retain the nodal displacement degree of freedom together with the additional degree of freedom for the pore water pressure. Consolidation analysis in SoilWorks assumes that all elements retain the degree of freedom for pore water pressure unless two boundary conditions, which are namely non-consolidation condition and draining conditions, are defined. So you must make sure that you utilize or you use these two boundary condition to properly define your exact material or drain property. Now, what exactly these boundary conditions are? Non-consolidating boundary: if the elements are not expected to subject to consolidation, for instance embankment materials, then you have to assign them with the non-consolidation condition. Okay. Second is the draining boundary condition. Now, if a draining condition exists in the consolidation analysis, the drainage condition must be followed. Once consolidation is carried out with proper boundary conditions, excess pore water pressure must become zero in the region where the non-consolidating and the drainage condition are assigned. For example, if you are using drains, so you will assign the draining boundary condition to the drains. Also, if the top and bottom layers of the clay, as you can see in the figure, you have to assign the draining boundary condition. What it says is that there should not be any excess pore water pressure, zero, in the regions once this boundary condition has been assigned. It will be more clear when I will elaborate you it in the demonstration part. Okay. Now let me move on to the program once again. So as you can see that SoilWorks is a bridge between both the types of analysis. So you can check a model with both 1D consolidation as well as finite element analysis, but there are few changes which should be incorporated. For example, the boundary condition and also the material property input. Now what we'll be using is that we'll be using the material will be modified camp clay. Okay, so once again the modeling part will remain same. What I will be doing is that I'll just import a DXF file. Okay. Now, as you remember, the next step will be the definition of ground material property. Now we have to use the Moore column and the Moore column to define the sand and embankment properties. And for clay, you have to input these parameters for modified camp clay model, which will include the over consolidation ratio, the slope of NC line, that is the normal consolidated or over consolidated line, and also the pre-consolidation void ratio, etc., as shown in the figure. So let me import the material property just to save some time from previously defined material property. So you can see that we have embankment, which has been defined with Moore column, clay defined as modified camp clay, and weathered rock defined as Moore column material model. Now we'll define smart surface. Okay. Now you need to assign the material property. So either you assign it to surface and then go for smart mesh, which all of you know, I hope so, that it is an automatic feature in SoilWorks where the program automatically generates the mesh for you. But today I would like to show you the feature auto mesh. Now here what you do when you mesh it, you simultaneously give the material property. So this is weather drop. Let us go with a size of 0.5, say apply. Similarly, select other layers. So this is clay 3 for us. Say apply. Clay 2. Say apply. Clay 1. Say apply. And finally, we have the embankment. Sorry, Control Z. So model. Okay. Now, whatever mesh set you have generated, you can see that you have different mesh sets for clay 1 with it basically has accumulated on the basis of the surfaces, clay 2, clay 3, weathered rock, and you have the embankment. Now you have to you have to give the boundary conditions. So the first boundary conditions will be the smart support, which is basically the ground support. So just GS and say OK. So it will be automatically generated by the program. Next is the draining condition. Now you know that the top layer and this is the bottom layer are basically clay, so you should provide a draining condition to the top of the clay and to the bottom of the clay, and just say draining conditions. Okay, and just say apply. Now let's suppose if you want to provide some drains beneath the embankment, so I'm just providing, you have to select this curves and then say once again the draining condition and give it a name, let's say drains. Say OK. Fine. Now next boundary condition which we have discussed is the non-consolidating boundary condition, where we are not expecting any kind of consolidation. So this is embankment for us, so just name it non-consolidating boundary condition. Just say non-consolidating boundary and just say OK. Fine. So these are the two boundary conditions which we have discussed and one should apply whenever you are going to use it. Fine. So next we'll go to the definition, construction stage definition. Now here once again we have three stages. Okay. First stage, second stage, and third stage. First stage will name it as initial, where there is ground with drains or without drains, and the time step will be 0 with 1 because we are not considering any steps because it is just the general step. We can just say save results. Okay, say OK. So say modify, and the water level we have to define. So what we can do is that we'll just use the water level definition to select the curves. Okay, now once again we'll go to construction stage. First stage, just name it initial. Water level, we'll select water level, just say modify initialize displacement. This is because the first stage, so we do not want any kind of displacement due to the self weight. We are just want to initialize the stress condition in the model, so we say initialize displacement, modify. The second is embankment. So for embankment, what we'll be doing is that the time step, let us say that 45 is the number of days in which it is constructed. So we'll divide it in number of steps, let's say 10, save result and say create step. So each of this stage will get what is the settlement happening. So just say OK. You need not define water level again, say modify. So the last will be the leave time. Leave time will be basically the number of final number of days after which you want to check. For example, 1000 days, the number of steps being 20. Save results, say create steps and just say OK. Now you can say modify. Okay. Now finally we'll define the construction stage. So at the first stage, we'll activate every mesh set except for the embankment. So this is the activated column. Then we'll activate the ground support condition. Okay. Draining condition and the drains. Now for example, once again, as we did in the previous uh, 1D consolidation analysis, once again you can deactivate the drains. Yeah, draining condition you can keep for the clays, but you can deactivate the drains and then study the influence. So after the analysis, I will just show you one more example where how you can interpret the results for the same. So with drains or without drains can be just done using activating and deactivating. So say apply. Second stage, you will activate the embankment and activate the non-consolidating boundary condition, say apply. And finally you have the leave time, so you need not do anything here, just say close. Generate an analysis case, say add, give it name, let's say construction stage CS. The analysis control data, you have to check in for this layer, no initial water level, because we have already defined it during the construction stage definition. So just say okay. Okay, close it. Now analysis and report, say perform analysis, save it. Now it will take some time to analyze. So what I will do is I will just open an already analyzed file to show you the results. Okay. So one we have without drains and with we have with drains. Okay, so these are the results which you get. For example, in the ground element stresses. So this you can see that stage 2 time step we have divided into. This is the third time step when the 1.1 times of the total load, that is we have considered a 45 days construction, then what is the load coming on that day, or we'll directly go to the final stage. So you can see the pore water pressure variation in the model. Also you can see the displacement contours. Okay, now the thing is how we are going to consider that what is our primary settlement, what is the secondary settlement, or what is the settlement as a result of uh, let's say consolidation. So here you have to extract the result. So I will show you. Go to result, you say extract. Okay, so we are interested in vertical displacement right now. Okay, so I'm just selecting a node beneath the embankment. I'm just selecting all the time steps and I'm just saying table. Okay, now with each time steps it is giving me a table. Okay, so what you can do, you can just export this to Excel, this values, and plot a graph. Okay, so this you can do for both, one without drains and one with drains. I already told you how to consider the both when while considering the construction stage definition. And after that, when you plot it, what you will get a similar kind of plot. Now with the drains, if you see that after a few number of days, that is something around 400, it becomes almost horizontal, I will say almost 600, that you have to plot it more accurately, or you can check it from the data. So you can see that after 510 days it is almost constant, 0.67 or 0.69. So there is some difference, but it is almost. So you can check that what is the percentage of consolidation at any particular day with the help of this graph. Also, without drains, you can see that the consolidation is still happening. So the at the end of 1010 days, with the help of drains, we were able to rapid up the settlement, which was something around 0.7. But at the end of 1010 days, without drains, it's still consolidating, or it's still the settlement is taking place, and the settlement which we are obtaining is 0.644, which is something around which we achieved already in 260 days with help of drain. So such kind of comparison could be made, and thus you can study the influence with drains and without drains in consolidation with finite element analysis. Now the advantage of finite element analysis is that first of all, it's a 2D analysis, that is even the settlement is happening, you get the contour plot in both the direction, as I will show you in the program. Okay, so this and also you get the pore water pressure variation, as I already told you in the program, that how the pore water pressure variation is taking place could be considered. Fine, so this can also be done. Okay, now finally moving on to the presentation part. In the results, in the finite elements results, now here what you can do, you can go for stability check for adjacent structures. If particular consolidation is taking place, which cannot be done in 1D consolidation, because there you will able to only consider the settlement in along a particular line. But here you can consider the whole model as a continuum model, and hence can study the effect on adjacent structure. Also, the calculation of the construction periods on stage embankments, if you are going for construction stage analysis, can be considered. And finally you get a settlement time plot, which helps you understand that what is the percentage or degree of consolidation which has occurred over a period of time, what is the primary consolidation as a result of the construction. So this can also be considered. So with this, I will conclude today's session on consolidation analysis. So just to summarize, we have dealt with a 1D consolidation and finite element consolidation in detail with demonstration in the product, and how you can basically check like the influence of drains with drains and without drains in the same model with the help of program. If you have any queries, you can write to us at techsupport@midasit.com. I thank you all for joining this session. And with this, I will conclude today's session. So once again, if you have any queries, kindly write to techsupport@midasit.com.